Hello, everyone. Today we are going to discuss the results of the basic tests we performed in our last video, Power Transformers, the Lost Art of Custom Winding. And we are going to try to perform some more tests to characterize our transformer according to the simplified model we described in the first video of this series, Power Transformers, a simple circuit model. The basic tests we performed in our last video showed that the transformer is delivering the right voltage on the secondary, is drawing a low idle current in the primary, is not overheating and has a better than predicted regulation. For applications like our isolation transformer and for most linear power supplies, this is enough to guarantee that the transformer we built is okay for operation. But these tests do not allow us to characterize the components of our model because the readings of voltmeters and ammeters alone cannot be used to measure the phase shift between voltages and currents imposed by the magnetization and leakage inductances. Wattmeters measure real power, and some also measure apparent power, reactive power and power factor, which is the cosine of the phase shift. All of these quantities are related and we need them to characterize the impedances as we measure them. Oscilloscopes can also be used for that purpose, and that is what we are going to use in this video. The first we are going to perform is the open circuit test. Connecting the oscilloscope like that, we can measure the voltage on the 15 ohm resistor, which will be the magnetization current multiplied by its resistance on one channel and the voltage on the primary on the second channel. Obviously we will have to invert the signal on the second channel because the ground of the oscilloscope, which is also its reference, is connected against the conventional polarity for voltage. Note also that we had to resort to a compatibly rated auxiliary power transformer to perform the role of an impromptu isolation transformer. A variac does not provide isolation. On the contrary, with a variac the primary is always electrically connected to the secondary. And that is why we stress for the nth time. Do not try this if you are not a qualified professional or work under the supervision of one, because you need to know what you are freaking doing. Be warned. Anyway, here we have it. The blue trace represents the primary voltage, the yellow trace represents the primary current. You can notice that the current is highly non-sinusoidal. This is the result of the core nonlinearities which we have already discussed in past videos of this series. But we are using a linear approximation to make our calculation a little easier. Note that the oscilloscope is already calculating its RMS value, printed on the lower left-hand corner of the screen. We divide this reading by 15 ohms to get our RMS current. The dark blue, or purple, trace, depending on your perception, is the instant mathematical product of the light blue and yellow trace. It is proportional to the instant power. The mean of this curve is proportional to the real power. To calculate the mean, math says I have to measure the area under the curve for a certain period and divide the result by this period. I could save this curve to a flash drive, transfer it to a computer and calculate it using a spreadsheet. But I will do it the old way and will calculate it by measuring the area as it appears on the screen. Well, that is the result of my measurement and the subsequent calculation. The core loss is about 5 watts, which is desirably below the prediction of 5.5 watts. Remember that at the time when we were designing our transformer, we estimated a conservative 2 watt per kilo core loss because we did not have the exact figure at hand. The result is highly satisfactory therefore. Using the power triangle technique, we can now calculate the reactive power and from that deduce R sub C and L sub M. Remember once more that these two modeled components are highly nonlinear and their values vary instantly as well as with amplitude, temperature, frequency and whatnot. Now it is time for our short circuit test. That is how we did it in the last video and now how we are going to do it. The issue here is that the transformer is already encased in a metal chassis with an on-off switch, a fuse holder with a 2-amp fuse, a power plug and a power cord. And we do not have access to the transformer leads anymore. But that will be no problem. We will use the values we measured in the first short circuit test to deduce the component values of our model. And here we have it. This oscilloscope screenshot shows the voltage as the blue trace and current as the yellow trace. Now we adjust the time base so that we can better measure the phase shift between the two quantities. And we use this value for the calculations, as you can see. Our sub H is the name I gave to the resistance added by the additional hardware we talked about, that is the switch, fuse holder, etc. This 7.7 volts here is what we measured with a multimeter in the last episode of this series. So we can calculate the wire loss of 11.5 watts, which is less than the 13 watts we estimated initially. Re-examining our preliminary guess, however, I supposed a load powered by the nominal secondary voltage and current at full load. That would require a slightly different turn ratio to compensate for the voltage drop caused by the wire resistance, and that would increase the primary current a little. Later I decided to leave the secondary uncompensated. This of course requires a different calculation, which would give us approximately 12 watts or precisely 11.6 watts. Anyway, the measured value of 11.5 watts is absolutely fine. And then we can calculate the real efficiency of this transformer, which is a little better than the 90% we estimated. And with that we can finally characterize our transformer like what you see here. Of course, you do not need to have all the trouble to measure this for every transformer you design and build. I did it just to give you an idea of what to expect in a device like this. So thanks for watching. Have a good night and stay beautiful.